In this video, we're going to measure the equivalent series resistance of a capacitor using an oscilloscope and a function generator. This also is called ESR. Now, ESR is really kind of a measure of effectively the resistance that looks like it's in series with the capacitor itself. Now, ideally, that doesn't exist, but for inexpensive capacitors used at high temperatures and with high ripple currents and things like that, many times the capacitors can begin to dry out, and when that happens, the resistance effectively increases, which causes heating, which kind of accelerates the whole process, and the capacitor ultimately fails. It's a pretty common failure mode. So we can model that ESR kind of like this simple diagram here. In reality, it's a little more complex than that, but for our purposes, this will do. The way we're going to measure the ESR is to essentially put an AC signal through the capacitor. We're going to pick a frequency that's high enough that the capacitor would ideally look like nearly a short, less than 1 ohm of resistance or capacitive reactance. So if there's any voltage drop across the capacitor, it's going to be due to the ESR and not due to the capacitive reactance, ideally. Okay. So we're going to use a function generator. Now, most function generators can be modeled kind of in this way, where you've got an ideal voltage source, in this case a square wave, followed by a 50 ohm output resistor, so that gives them a 50 ohm output impedance. Now, it's going to be important to know what the output impedance is, or at least to verify that yours is 50 ohms or something else before you go do the measurement, but because we're going to use this later on when we go to calculate things. When we set up the function generator, we're going to use a frequency, I like somewhere between 100 and 300 kilohertz. Because at that frequency, the electrolytic capacitors that we're typically interested in will have a capacitive reactance less than 1 ohm. If we pick 200 kilohertz, you're looking at typically 10 microfarad or larger capacitors. Their reactance is going to be low. So a good capacitor is going to look like a short, and it's not going to generate any voltage across it when you connect it up to the function generator. But this frequency is also low enough that we can kind of ignore any transmission line effects, reflections, and that kind of thing. We don't have to properly terminate the lines and such. So that's a pretty good compromise. Now, I'm going to use a volt peak to peak because that's pretty good for out-of-circuit testing. If you really want to try doing in-circuit testing, you probably want to go to 200 to 300 millivolts peak to peak maximum, but I don't really recommend in-circuit testing. So let's take a look at how we're going to set this measurement up. Okay, in order to set this up, the first thing we're going to do is set the amplitude of our function generator. And we'll just connect it right up to the scope. You can use a probe, or you can go right into the high input impedance input of the scope. Again, we're using a low enough frequency that we don't have to worry about putting a 50 ohm termination there. So what you want to do is set it up for about 200 kilohertz, and the voltage to vary between ground and your peak to peak voltage, say 1 volt peak to peak, and then back down again. You don't want to go below ground and reverse bias our capacitor under test. So we do that first. The next thing we can do is simply put our capacitor under test right across the output of the function generator. And we'll do that right at the front at the input of the scope, and I'll show you how we'll do that. Now, ideally, the capacitor should have no equivalent series resistance, and the capacitive reactance should be well under 1 ohm, so that as soon as you connect that capacitor up, the output as seen on the scope should go to nearly nothing. Okay. Now, what will happen is if a capacitor has some equivalent series resistance that's measurable, a couple of ohms or more, the capacitor might look like a short, but the ESR component will not, and a voltage will be generated across that. And by measuring that voltage with the scope, and then it's a simple voltage divider calculation to extract what that equivalent series resistance is. But the reality is that oftentimes, as these capacitors dry out and the ESR goes up, the capacitance also goes down. The capacitors will be reduced in value. So what will happen is this capacitor might get low enough that you'll start to see the RC charging time constant, instead of a nice low impedance. And you can see a combination of that, and I'll show you what that'll look like in a moment. Now, many ESR meters, including the one that I built a few years ago and did a video on, I'll put a link to that, by the way, down below, will measure the response of that RC exponential as well as the ESR. But at the end of the day, that's okay, because in either case the capacitor is bad and you're going to want to replace it. So here's what we're going to do. We're going to have our function generator. We'll start off by measuring just the voltage without a capacitor connected to it. But then when we connect our capacitor up, we're going to see one of two things. We're either going to see just a reduced square wave on the scope, and then the voltage there is really the voltage across the resistance, the equivalent series resistance, because the capacitor looks like a short at those frequencies. But oftentimes what you'll see is a combination of the effects. You'll see a step change that's due to the ESR, but you'll also see an exponential rise and an exponential fall on either end of the step change. That indicates that you essentially have got a much lower value of capacitance, and you're seeing essentially the RC time constant of this combined resistance and the capacitance. But in either case, what this is showing you is you're going to be generating some voltage or dropping some voltage across this capacitor, when ideally it should look like a short and you shouldn't develop anything. So this is the arrangement we'll use to make the measurements. The end of this coax here runs back to my function generator. It's back over my shoulder. And I'm just going into a little BNCT. One end that I'm going to couple right into the scope input, and the other end connected up to a set of mini clip leads that we use to connect to our capacitor under test. So without anything connected here, if we just hook this up to the input of the scope, I can see the response of my function generator. I'm at 200 millivolts of division, so that's 5 divisions. So I've got 1 volt peak to peak, and if I momentarily couple the scope to ground, I can see that's where ground is. So this voltage is varying from ground up to a volt and then back down to ground. So again, we're not reverse biasing it. So that's the proper setup to get ready to make the ESR measurements. Alright, starting off with a good capacitor, so you know what you want to see, is we're just going to take this 220 microfarad capacitor. Note that this is the indication here for where the negative lead is. So we'll connect the black mini grabber lead up to that, and then we'll take the other lead and hook it up to the other end, and watch what happens on the scope screen. So we've effectively, nearly completely squashed that signal. We're going to see the average value of it, and that's normal. We're also going to see a couple of little blips right at the edge transitions, and if we look carefully, if I turn the intensity up, I'm able to see those little blips here and here and here. Now that's normal. What we're looking at is the fact that we're not terminating this coax properly. There's a little bit of reflection coming back off of these leads, a little bit of inductance in series with the capacitor, so you're going to get that, no big deal. But ideally what we've seen is that we've taken the top and brought it down, the bottom brought it up, and those two are effectively at the same level. If there was some effective series resistance there, we would have a difference between the high and the low level. So this is what a good capacitor looks like. So let's take a look at even a little bit closer in here. What we can do is change the scope to be AC coupled. Alright, we'll move our position up, and then turn up our volts or turn down the volts per division to get a little bit more magnification on this. And now you can actually see, a little bit of the the step change due to those inductance components that we talked about. I can see a very small change. In fact, if we go to even smaller, I can see a very small change here. I'm at 10 millivolts of division. Okay, so we can see a very small voltage change here. In fact, if we put a couple of voltage cursors on here, we can go take a look. I'm measuring about 3 millivolts. So we've taken that 1 volt peak to peak square wave and reduced it down to 3 millivolts. That's pretty insignificant. This is pretty darn close to a short. So we're looking at well under 1 ohm of equivalent series resistance with this good capacitor. So let's go look at one that's not so good. Now this is actually a good capacitor, brand new. It's just physically a lot smaller. And typically as the capacitor gets smaller, for the same value, they're going to have a higher equivalent resistance. And you can see that here on the screen, that this one is dropping about 8 millivolts, 9 millivolts from that 1 volt peak to peak signal. So while it's not a bad capacitor, the capacitance is still good. It's just the fact that it's physically smaller, you will naturally see a larger ESR because the plates are physically smaller and will have larger resistance. But this is the same type of shape that you'd see. It just might be larger in amplitude when you've got a capacitor that has even a higher series resistance. So let's go look at a capacitor that I pulled out of an old monitor that actually failed. Well, see, now with this bad capacitor in here, I've actually got to bring my volts per division back up again so I can actually see what's going on. So with this one, we can kind of see that effect that I mentioned earlier, where we have a step change due to the ESR, but then an exponential change due to the reduced capacitance. So this was a failed capacitor. If we look carefully at it, you might be able to see that the top of it is domed out. It kind of got hot and overheated and dried out. It's just a nasty capacitor. But if we look at the peak-to-peak voltage of this, say from down here all the way up here, we're at about 100 millivolts. So that 1 volt peak-to-peak signal was only brought down to 113 millivolts here now. So this capacitor is certainly bad. Now what's funny is that if you measure the capacitance of this, it might look larger than you might appear from this RC time constant, but that's just due to the fact that when these things dry out, the resistance is not, or the resistance increase is not evenly distributed across the plates, and you get a little bit more of a complex thing going on. But at the end of the day, that would be a bad capacitor. Leaving that on the same scale, just to kind of give you some perspective, let's go back and take our good capacitor and take a look at what that one would look like under that same scale. Okay, so on that same scale you can see how much better this capacitor is. So if you're interested in trying to calculate out what that equivalent series resistance is, just stick around for the next part of the video. If not, that's basically how you do the measurements. So let's go take a look and see what those calculations look like. It's really quite simple. All right, to calculate the equivalent series resistance, it really is just a voltage divider calculation, right? We're looking for this resistor value. We know what this function generator ideal voltage is. We know the output impedance is 50 ohms. We just don't know the R. So that typical voltage divider calculation would be, the function generator voltage multiplied by that resistance divided by the sum of the resistances gives us that voltage, which we'll call VR. Now we know what VR is. We've measured it. Okay, we know what the function generator voltage is. We've measured it. We just need to solve for R. So we can simply run that equation, or rearrange that equation like this. And we got to rearrange the equation as such. We wind up with this equation here that says the ESR is equal to the measured voltage across the capacitor multiplied by 50 divided by the open circuit voltage of the function generator minus VR, or our measured voltage. So let's run that calculation for the bad capacitor that we measured that was putting 113 millivolts across the across itself. Okay, so we know we measured 113 millivolts, and we'll multiply that by 50, and then we're going to divide that by we got 1 volt peak to peak minus the 0.113 volts. Divide that, we wind up with about 6.3 ohms of ESR for that particular capacitor. Let's go take a look at what I measure on my homebrew ESR meter for that bad capacitor. Here's my little homebrew ESR meter. Let's make sure that it's zeroed properly. We'll short the leads together, and it looks like we're zeroed properly there. And so let's connect up that bad capacitor. So I've got the negative lead going to the negative side, positive lead to the positive side here. If we take a look, it's actually you've got a little bit of parallax. You're looking off to the side from here, but if I pull this over, you can see it's just a little bit greater than 5 ohms, close to 6 ohms there. So this meter is basically measuring that peak-to-peak value, or pretty close to it, of that response that we're seeing on this bad capacitor. And again, a lot of ESR meters will do that, but at the end of the day, that value is much higher than you'd want to see on a good capacitor. If we connect up my good capacitor here, that same way. Okay, so here's the ESR of that good capacitor. You can see that looks pretty darn near a short. So if you don't want to go and build one of these things, and you have a function generator and an oscilloscope, you can very easily measure what the ESR is, or just at least to check whether a capacitor is good or bad. Anyway, thanks for watching, and I'll see you later.